Alright guys, how's it going? Mike coming back at you here with another video on vector calculus. In the previous video, we looked at the properties of the derivatives of differential forms. How do we differentiate a 0 form, a 1 form, a 2 form, and a 3 form? And we went through a couple examples to see how we use those properties of differentiation. In this video, we're just going to go through a couple more sample problems here just to help us get more used to finding the derivative of a differential form. And we're also going to revisit a formula that we saw earlier on in this section. And it's really important that we get good with finding the derivatives of differential forms because that plays a starring role in the next video that we are going to see. So we have a sample problem here, so let's get right into it. Let alpha equal p of x comma y dx plus q of y comma z dy minus r of x comma z dz. And we're going to find the differential of alpha, or the derivative of alpha. So p is just a function of x and y, q is just a function of y and z, and r is just a function of x and z. So I want you to try this problem on your own. Refer back to the previous video if you need to. Look at those properties of the derivatives of differential forms. Once again, use those to figure out what d alpha is going to be. So pause the video here, and once you think you have it, press play, and we'll see if you were right. All right, so let's see if you were right. As we begin to find the differential or the derivative of alpha, recall the linearity property that says you can take the difference or sum of these individual one forms, and when you take the derivative of the difference or sum of these things, you can break it up at the plus or minus signs. So I'm going to find the differential of p dx plus the differential of q dy minus the differential of r dz. And writing p dx is the same thing as p wedge product dx, and so on with q dy and r dz as well. So we're going to find the derivatives of these three separate terms here. This is where our most important property of differentiation comes in. We're going to be using it 3 separate times, going from this line to the next line. When you take the derivative of the wedge product of two things, it's d of first thing listed, wedge second thing, plus -1 raised to the power k times first thing wedge d of second thing listed. And k here is whatever type of form you have that is the first thing listed here. Now, for the most part, pretty much any problem that you're going to see from me, the first thing that you're going to write is a 0 form. So when it comes to putting the sign in front of that second term that you get, it's pretty much always going to be a plus. So going from this line down to the next, so we see that we did the differential of the first thing listed, wedge the second thing. So that's our first term that we get from the first term in the top line here. And now plus, because p here is a 0 form, k equals 0, so we have -1 raised to the power 0, which is just 1. So plus the first thing, p, wedge d of the second thing. So this is how we get these two terms in the bottom line from the first term in that top line there. And we're going to do the same kind of thing with these other two terms. If I take the derivative of q wedge dy, it's going to give me dq wedge dy, and plus once again, and this is a q there, my apologies, q wedge d of dy. And then minus dr wedge dz, and I multiplied the minus sign into both terms, so we have minus r wedge d of dz. So this is what we get just using that distributive sort of property, if you will, of differentiation of differential forms. Now, I want to look at some of these terms here because we're going to find that some of these terms nicely cancel out. Recall that if we take the differential or the derivative of any basic one form, we get 0. d of dx, d of dy, and d of dz are all equal to 0. So we have a d of dx, a d of dy, and a d of dz right there. So all these terms are just going to vanish out to 0, and we're left with these three terms. Now we're going to find the differential of our functions p, q, and r. Well, p is only a function of x and y, so the differential of p, using property number 1 of our differentiation properties, is going to be the partial of p with respect to x times dx, plus the partial of p with respect to y times dy. And it's that whole thing, wedge dx. Similarly, q is only a function of y and z, so the differential of q is going to be the partial of q with respect to y times dy, plus the partial of q with respect to z times dz. And we have this whole thing, wedge dy, minus partial of r with respect to x times dx, plus the partial of r with respect to z times dz, because r was only a function of x and z, and that whole thing, wedge dz. Now we are going to use our wedge product here. This dx is going to be multiplied into each of those two terms, and the dx is always going to be listed second in the order of our basic one forms. So dy there, and dz there and there, and that gets us down to this bottom line here. So we see we have some partials of these functions times the wedge products of our basic one forms. We know from the properties of the wedge product that if we take the wedge product of a basic one form with itself, we're going to get 0. So that term is gone, that term is gone, and that term is gone as well. And the other thing we have to do now to finish this up, we have to make sure that these basic two forms that we have are in the proper cyclic order. Again, it's dx dy, dy dz, and dz dx. Here I have a dy dx. I need to switch those. When I do that, I multiply by a -1. I have a dz dy. I need to switch those. Again, multiply by a -1. And here I have dx dz. I need to switch those. Again, multiply by a -1. And when you do that, you come up with your final answer, which is partial of r with respect to x times dz dx, minus the partial of p with respect to y times dx dy, minus the partial of q with respect to z times dy dz. Recall that when you take the derivative of a k form, where k is 0, 1, or 2, you get a k plus 1 form. When you differentiate a 3 form, you get 0. So we started off with a 1 form, we ended up with a 2 form, so we know that this is what we should get. This is a very realistic answer. So this was a first problem, working with differentiating a 1 form. Not the most complicated thing here, but still really good practice. In the next problem, we're going to see how we take the derivative of a 2 form. Okay, so we're at our second problem here. let omega be a 2 form, that is p of x comma y dx dy minus q of x comma y dy dz, and we're going to find the differential of omega. We're going to find d omega. Once again, just note p is only a function of x and y, as is q here. So once again, pause the video here, use those properties of differentiation for differential forms, try to figure out what d omega is going to be. Once you have think you have found the answer, press play, and we'll see if you were right. All right, so let's see if you were correct in the answer that you came up with. The differential of omega, again, we're going to use that linearity property, and we're going to break omega up at the minus sign, and we're going to find the differential of p wedge dx dy minus d of q wedge dy dz. Again, we're going to use that distributive type property of differentiation for differential forms to figure out what our terms should be here. So, d of first thing, wedge the second thing. There goes there's our first term there. Plus negative 1 raised to the power k. But once again, the first thing that we have listed is a 0 form. So negative 1 raised to the 0 power is just 1. So it's plus, first thing listed, the p, wedge, d of the second thing. So there's the second term that we get there. And then same type of thing is working for the second term here. The dq wedge dy dz, and then I once again multiplied the minus into each term. So we get minus q wedge d of dy dz. Now, looking at these terms right here, these that are underlined, we saw that d of dx, d of dy, and d of dz are all equal to 0. You could check pretty straightforward that d of any one of our basic 2 forms is also equal to 0. d of dx dy, d of dy dz, and d of dz dx are all equal to 0. If you use our distributive type property for differentiation of differential forms on each of these guys here, you'd be getting d of some basic 1 form, wedge another basic 1 form, minus the first basic 1 form, wedge d of the second basic 1 form. And d of any basic 1 form, as we know, is 0. You're going to be taking the difference of the wedge product of something times 0, and the whole thing is going to just come out to be 0. So add these guys onto your list of tips and tricks to know in regards to differentiating differential forms. These guys are all equal to 0, which means that these 2 terms right here are going to vanish out. So we're only left with dp wedge dx dy minus dq wedge dy dz. We're going to write the differential of p and the differential of q. P and q are both functions of x and y. So we get p sub x dx plus p sub y dy, wedge the dx dy, minus q sub x dx plus q sub y dy, wedge the dy dz. Now we're going to multiply our basic 2 forms into each of our basic 1 forms in these terms here. Again, we're going to keep the consistent order. So in each of these terms that we get, we're going to write the basic 2 form after the basic 1 form. And we can use our associative property to group the wedge products. That's going to lead us to right here. So we have 4 terms, p sub x times dx wedge dx dy, plus p sub y times dy wedge dx dy, and so on and so forth. Thinking back to getting practice with our wedge products, we said that if you have to take the wedge product of a 1 form and a 2 form, and in each of these things you have the same basic 1 form showing up, you're just going to wind up with a 0. And that's exactly what we have happening in this term, and this term as well. So these 3 terms are all going to go to 0. And we're only left with 1 term, and we're left with a 3 form. And since we start off with a 2 form, and we know that if we differentiate a k form, we get a k plus 1 form, this is a logical answer. We just have minus the partial of q with respect to x times dx dy dz. So this is our other practice problem in regards to differentiating a 2 form. So a little bit more work kind of going on here, but with the use of our wedge product properties as well as our new little tip or trick that we learned, we can make it a pretty short and fairly straightforward process here. Now I want to revisit the formula for the integral of a 2 form and a specific aspect of it that perhaps at the time when we first saw it, it wasn't quite clear why it was what it was, but now that we're armed with the knowledge of differentiation of these differential forms, we can see why this thing would be what it is. So if you have a surface, it's parameterized by capital phi hat, x, y, and z are each functions of u and v. We want to show that dx dy is equal to partial of x comma y over partial of u comma v du dv. Just as a quick recap, note that that guy right there is the determinant of the Jacobian matrix. The Jacobian matrix, again, is the matrix of partial derivatives of x and y with respect to u and v. So we want to see how dx dy is equal to this determinant of a matrix of partials times du dv. So dx dy, same thing as dx wedge dy. Since x and y are functions of u and v, we can talk about x and y each as 0 forms, and we can then take the differential of these 0 forms using our previously stated property. Dx is the partial of x with respect to u times du, plus the partial of x with respect to v times dv. Dy, the differential of y, similar. So we're going to take the wedge product of these things here. We're going to FOIL this out. And again, the 0 forms, the partials of x and y with respect to u and v, we can multiply those together, that's fine. But the du's and the dv's, we have to maintain the proper order. And when we maintain that proper order, and we write it as the sum of 4 terms, we get x sub u times y sub u, and then du wedge du, x sub v times y sub u, and that's times dv wedge du, plus x sub u times y sub v times du wedge dv, plus x sub v times y sub v times dv wedge dv. When we take the wedge product of a basic 1 form with itself, we get 0. So those terms are out. And our cyclic order here is du dv. So with this being a dv du, I need to switch this guy switch these two guys, and I'm going to multiply by a -1. So that is going to give me x sub u times y sub v minus x sub v times y sub u du dv. And that guy there is the determinant of a matrix. Specifically, that matrix there. If you take that determinant of a 2 by 2 matrix, you do indeed get that determinant right there. And this 2 by 2 matrix here, that is the Jacobian matrix of partial derivatives of x and y with respect to u and v. So this is why we say that dx dy is equal to the Jacobian determinant of x and y with respect to u and v times du dv. Now, by a similar process, we can show that dy dz is equal to the Jacobian determinant of y and z with respect to u and v, and dz dx is equal to the Jacobian determinant of x and z with respect to u and v. So if we make these substitutions into the integral of a 2 form over a surface, we substitute in the dx dy, dy dz, and dz dx results. Just substituting in those Jacobian determinants, we get the right-hand side right here. And that is the formula that we saw earlier on in the section when we talked about the integrals of differential forms. So at first, when we saw this, it may not have been clear as to how we're bringing these Jacobian determinants in there, but armed with the knowledge of differentiating differential forms, we can now see why the formula is what it is. We can now see why this thing would make more sense. And these results here, dx dy, dy dz, and dz dx being equal to Jacobian determinants times du dv, those results are going to be very, very important for the next video. When we finally get to the big theorem that we want to get to in this section. It's the big theorem that ties all of the major integration theorems in this course, as well as from previous calculus courses. It ties all these things in together, and we see how all these special theorems that we thought that before perhaps were not quite related to each other, we see that they are. So that's what's coming in the next video, but this was just a video to get us a little bit more practice with finding derivatives of differential forms. That also is going to be key to the next video. If you have any questions or comments, be sure to drop them in the comment section below. Otherwise, until the next video, folks, take it easy.